Can you hear me? All right. So here's the problem we had from last time. We had a rectangle, and the constraint was to fix the area. Okay. And just by doing first order optimization, we found that the best shape is the hypercube, the cube. So the shape that has the most surface area, A, where's the number? Is given by a square root of the surface area over 6. So that's the rectangle with the optimum volume given a surface area. All right, good. But we have to prove that this is the global minimum. Okay. So for this, you need second order conditions. So let me remind you. So these are the second order conditions. First one, we showed that our rectangle attains it. So a solution for this guy is the one we found before. But then to show that this is a valid minimum and not just stationary. So again, remember from the quiz, stationary does not imply minimum. It could be saddle point, right? So same thing here, nothing changes. We have to check positive definite. Okay, so I'll do that in the example. All right. Okay, so we had a minimizer, namely the cube with length equal to square root 6, square root a over 6. And lambda was the Lagrange multiplier. Okay. So now we have to show that this is indeed a minimizer. We already found the gradient. So this is the grade, F is the volume, so X, Y, Z. And this is its gradient of constraint. Now I need the Hessian, because we're going to check positive definite. So this is the Hessian, and then you evaluate at the point x naught equal y naught z naught. So this is L, L, L. So you get this matrix, and we do the same for the constraint, because we have a constraint of a surface area. Good. So I have to prove that this matrix is positive definite. Okay. How do I do that? Do you remember? I have a nasty way, but there's an easy way that we can do it. What? Okay, yeah, so leading minus, right? So you have -1 and then you will have to compute a 3 by 3 determinant. Okay, but let's do it. Question? Okay. So, but of course, I need the uh, anyways. So 2 lambda minus 1, you plug in your Lagrange multiplier that you found, and you plug in all your numbers. This is L. I should have written L. It looks like a 1. Anyway, so you put all this stuff in, and you get 6 minus 12, which is negative. So for this matrix to be positive definite, you need this matrix to be negative definite. Okay? Is that okay? So let's do that. Namely, you want to show that this guy is negative. Okay? All right. So I don't like it. Can we do it with leading minors? Oh no, I have to do it this way. Oh, yeah. So I have to do it this way because I'm only allowed to take vectors from the tangent space. That's why this question is hard. Okay. Yeah. Otherwise, I will just compute a determinant. All right. Anyways, so I plugged in that, and it gave me this polynomial. And now I have to give you the tangent space. So let's find the tangent space. So recall that we can use the trick. Recall that we can use the trick that Tx naught of the manifold is contained at Tx naught. So, and this guy is hard. I don't know if you remember, these are all the V's that are equal to some differentiable curve, right? Something crazy. But this guy is easy. Here you just have to find the vectors that are dotted to the constraints. This is easy. So we can ensure that our matrix is positive definite here, which implies it for its subset. Okay, good. So this is the tangent space. You only have one constraint, so you just have to satisfy this, right? So let me remind you what the gradient was, because I forgot. Yeah, so the gradient of this was 2L111. This was the constraint that, what was it? The surface area. So something like 2xy, 2yz, 2xz equal to A. That was 8. Okay, anyhow. Good. So this guy, let me write it for you. So it's 2L111 times V1, V2, V3. So you get this guy times 2L, but 2L is not 0. So you just get V1, V2, V3 equals 0. Is that okay? Okay, good. Questions? All right. So that's it. So any ideas what this looks like in 3D? What is it? What's the shape? Good. It's a hyperplane that crosses the origin. Because when they're all 0, they're 0. So I will put my, okay, let me do this right. It will be some plane that hits 0. Okay, good. That's fun. All right, what else? Oh, yeah, we're not done. We have to connect it. We have to show positive definite And that means you have to relate this crazy looking expression to your tangent space. So I want to prove this, right? That's what I want to prove. Want to prove. Good. All right. Let's go. So here's a dirty trick. We're free to use this. I mean, this is a very simple thing. So we know that this guy is 0. So the product is 0. And so that's good because we want to show that this guy is negative. Now, I even answer it. Okay, but okay, let me ask you, what do you think you get from here? Yeah, from here. Why do, why do I get, I skipped one slide, all right? Well, let's see if you're paying attention. I want to show that this guy is negative. Why is that the case? Not you. Sorry, what? Yeah, perfect. Yes. Good. Simple stuff. That's it. It's a broad course. Don't get scared. All right. That's it. That was the condition. So you might ask, well, how did you even think about this? There's no easy way. This was just a trick. I don't have a trick to, yeah, there's no systematic way to do this, unfortunately. No, there isn't. There isn't. Okay. Let's see, what else? All right, so that showed that your guy is positive definite. So again, let me remind you, we wanted to show that this guy is negative definite because we already had negative. So we went and studied the tangent space. The tangent space satisfied V1 plus V2 plus V3 is 0. And we used this to get this. Okay? That was basically the argument. So indeed, the cube is the global maximum. So it gives you the most volume given a surface area A. And it's a global minimum, but we're not going to do that. I see. All right, fine. But you can do it. I don't know why I said that. Because, like, let me think about this. You just need to show convexity for your problem. So, but anyways, we'll talk about it. And yeah, anyways. Okay, here's another example. This function, which is not convex, so you cannot use nice arguments. But we have a very beautiful constraint, y equals 0. Right. And we're doing, yeah. So can someone tell me what's the first order condition for this? Huh? What's the Lagrange multiplier formula? You don't need it for today, you need it for next week, but it's good to know. For life. Yeah, what should I write? Yeah. So what is gradient of f? And then what about this guy? Huh? Yep. So did I write? Oh yeah, good. Yes. So that's the one. And then do you want me to solve it? I'll solve it. So we have 2x is 0 and minus 2y plus lambda is 0, right? So So yeah, anyways, so this is a solution, and that's right. So now
I have a question.
I have to show that this candidate 00 is a strict local min. So I have to show that this matrix is a positive definite on the tangent space. So question, is this matrix positive definite? Why not? What are the eigenvalues? Yeah, I know. I'm just asking. I don't know. But okay, what kind of measure? Suppose I didn't have a tangent space. What would be the 00 would be what? If there was no tangent space. Final point, yes, good. Thank you. Great. All right. So, but that's not what we're looking. We're only constrained on the tangent space. And I know I just wrote it, but let me justify it. So once again, you just have to look on the bigger space, and the bigger space is all the v's in R2, so that gradient of GV is 0. Okay? And gradient of G is 0, 1. And you dot it with V1, V2. Okay? So you get V1 is, oops. You get 0 times V1 and what? 1 times V2. So what does, is that okay? What? Oh yeah, it is plus. Yes, yes, thank you. Good. All right. 0 V1 plus 1 V2. So V will be of the form what? This guy, right? So that's it. That you found the tangent space. Now you have to check that that this matrix is positive definite. So I take V1 0, 2 0, 0 minus 2, and V1 0. Can someone tell me what this is equal to? What do you think? What? When solving for x, yes. When solving for x and y, we also include the constraint. That's right, and I did. Constraint was g. Oh, okay, so what is it? Is it hard? Like this, like this. So you get this, and then yeah, 2v1 squared, which is strictly positive when it's not 0. And that's all you wanted. So indeed you get, which are, okay, good. Yes, never mind. Good. So you have positive definite on the tangent space, which is all that matters. Good. All right. Good. So anything else? Yeah, strict local min. All right. So how many of you took 236? Anybody? 236. Yeah. Okay, good. So at least one person will remember. So we have a notion of duality, dual problem. Do you remember this? So it's still true in null problems. We won't go too deep into it. I will do this. and I do it next week as well. And I have to do it. I mean, it's basic material. So, okay. So duality, let's talk about it. We start with the minimization problem with constraints, right? This is our setting. And we are going to consider this function, g lambda, and this guy, if you Google it, is called the Lagrangian. Okay. And so, yeah, we're gonna move from studying the mean of f of x to the maximum of g lambda. Okay, this is called duality, and you change one problem for another. So this shows up many times. People will go from an easier to a harder one and back and forth, or they can solve two problems at once because they have the same maximizer. So this guy is called Lagrangian dual function. This is 11.6 in your main book. All right. This function is concave in lambda. Any guesses why? Why is this whole function concave? It's a little bit tricky. Huh? Right. I don't know if you remember, we had this result that we had the following result. If I should use different notation. Okay, what shall I say? Call it capital Fi. If f, x, y are convex, then g of x equal to the supremum of f of x, y for y in some convex is also convex. Okay, now if you take minuses all over the place, it says that f concave implies gx equal to infimum of f is also concave. Okay, so when you take maximum of convex, you're still convex. When you take infimum of concave, you're still concave. If you take infimum of convex, you might not be convex. If you take infimum of supremum of concave, you might not be concave. Let's do some. Shall I do it? Some stupid example. So x squared is concave, convex. Same thing for this guy. Now take infimum in y. Okay, I mean this turns out to be x squared. So it doesn't, I don't know. If I think of what's a stupid example? I want to be non-convex. Maybe put a minus. Let's see, it will be 4200. Like this? No, okay, I can't think. How about this? How about make it plus? Like this. Is that okay? This is convex because if you take two derivatives, Well, it has a zero, but it is fine. It's fine. It works. This one is okay. Because convex allows to be, I didn't say strictly convex, so you can have a zero. Anyway, so this shows you that infinite does not preserve um, convexity. All right, moving on. So this guy is concave. That's why it's an amazing object. Because why? Um, let me say it here before I move on. Well, actually, it shows up later. But just to remind you, infinite of convex exists, and the same is true for supremum of concave. All right? And we're going to take the supremum of G lambda. So by concavity, we know it will exist. All right. We'll come back to this. We'll keep talking about this problem. So let me do an example. So this function given this constraint, I'm going to write down the dual function. So what do you do? You compute the Lagrange multiplier, right? So remember, you put your cost and you put your constraint, right? So you rewrite this as h equal to ax minus b. Okay, is that okay? Very good. What happened? Huh? What are you lost? Fx is the guy you minimize, like x squared. Yeah, it doesn't have to be convex, yes. But this function is concave because you study it in lambda. And this function is concave in lambda. Oh yeah, it doesn't depend on lambda. Yeah. Yeah, okay, yeah, that's a good question because we kept talking about this convex infimum. That's right. You should think about this as a function of lambda. Yeah, very good. Yes, all right. Okay. So later on today, I hope, I will show you that this infimum can be computed and you get this function. So you get your G lambda. All right, so let me give you a result of why we care about this. So here's the result. It's called weak duality. Okay. So suppose you attain the maximum at some point x star. Okay. Or the minimum or whatever it is, minimum. Yeah. Then the G lambda gives a lower bound to that value. Okay. And everybody okay? But then when the maximum attains it, it said that you have strong duality. Okay, so that means that if you want to solve minimum of f of f given hi 0, it's the same as solving maximum of G lambda. And this is amazing because lambda is unconstrained. Right? This is constrained. This is not constrained. You understand? So there's stuff like that happens. Anyway, so but what people mostly use is weak duality because strong duality is very difficult to get. If you took 236, this is the same as Slater's condition. So this is 236 APM. So I'm doing the same stuff, but for nonlinear things. Okay, so let's prove this lower bound. And just from that, we'll get many results. All right. All right. When a point is feasible, meaning it satisfies the constraints, we have the following. We have that the f of y plus the summation is equal to f of y plus summation of lambda I 0. So it's just f of y. Okay? Right? On the feasible points. So now taking Phenom over the feasible. Oh, okay, let me just, I haven't written it. So taking Phenom over entire domain. Okay. And we'll use the following fact. If A is inside B, then infinity of a function, capital F, in A is less or equal, other way, is less or equal than infinity in A. Because suppose this is B, suppose this is A, this could be an infinity, but there might be an even smaller value over here. Right? That's all. So that's what happens with infinity. And right away, this gives you the lower bound. So I have infinity. We just showed that these are I should write something else here. So let me correct this. Let me rewrite this for you. So this would be less or equal than infinity of lambda y lambda over the hi equals 0. Okay? I'll retype it as well. And we just showed that this is equal to infinity of hi equals 0 of f of y, which is equal to p star. Right? Good. And here I took that this is D, and inside you have the constraint space, hi equals 0, right? So, okay. All right, good. All right, so let's, let me do the example. This is too abstract yet. Let's do an example, we'll come back to this. All right, so here's the minimization problem. And I'm gonna find the dual problem, and I'm gonna solve the dual and get the solution to this. Okay, so I'm gonna try the way of solving this problem. And note that this matrix A is not even squared. So forget about determinants and all that stuff. Symmetric matrix, well, everything's out. All right. So I have to compute for you this dual. Okay. So meaning I have to take the infimum over x for this guy. All right. Right, yeah, that's a good question. So why is this guy convex? Any ideas? I mean this guy here. Why is it convex in X? What's the, you can do it by hand, or you can tell me what the Hessian is. What happens when you take double derivative here? Yeah, so you have a 0. And what about this guy? Huh? It's just the identity matrix. Why? Because this is equal to a half of summation xi squared. The gradient is equal to x1 to xn. And then, so this is the gradient plus, or minus, no, plus lambda a. And then, yeah, this guy dies out and you just have identity. Okay, good. So, and this is positive definite. So you have convexity, strict convexity. All right. Good. This is the constraint. Sorry, what? Yeah, we're talking about, yeah, I mean, that's why duality is very beautiful. There are no constraints here. So I integrate, I put the constraint inside the function. This is like a penalty. It's called the penalty approach. Because when this guy is away from being 0, you pay for it by this being positive or negative or whatever. Is that okay? So what was your question? Yeah, but here the guy died out. Yeah. Yeah. All right. So it has a unique global minimum by convexity. And let's compute it, which I think I just did. Let me do it again. So you have summation of xi squared a half, and then you have lambda of transpose ax. What's a nicer way to write it? I can write it as ij lambda j aij xj. How about that? Minus b. Is that okay? I don't know. I mean, should I do it some other way? I can do it with directional. It doesn't matter. So if I take derivatives, the first guy becomes x1 to xn, and then yeah. So second guy, you kill off the j. So you have summation of I1 to n, lambda I, AI1, AIN. So this is basically X. Like a lambda over here, right? Yeah, yeah. Oh, this guy is dead. Yeah, thank you. Does this have a nice form? So this is like lambda dot. I don't think so, right? So this is E first vector, second vector, third vector. How would you do it? Yeah, you can do it like that. You do it like this? I don't know. I think it's like this. Yeah. Anyways, this guy will die, so I don't care. And then if you take Anyway, so this is that's the gradient. So yeah, okay. So I didn't get it right. It was A transpose lambda. Right. So this guy is equal to X plus A transpose lambda. All right. So this is A transpose lambda. Okay. And then you set it to 0. So you get the stationary point, X equal A minus T lambda. Okay. No inverse, because we cannot really take an inverse. It's not squared. I mean, we can, but you use formulas like determinant. You can't. Anyways. So I have to do. Oh, I see. So I just plugged it in. Fine. So you found your candidate. So you plug it in. Right? Because now this guy is equal, call it X star. This is equal to lambda X star. Okay. So I plug in my guy. Hopefully I did it. Yes. So this is the dual function for your problem. Okay. And I know it looks terrible, but can you tell what amazing thing happened in this new problem? So suppose I take a minimum of this. What advantage do I have compared to before? Something changed. So minimum over lambda. What's the benefit of this new form? Something changed. What is it? What do you know about AA transpose? Perfect. All of that. Yes. So this was a homework in 2 to 4. This is an amazing matrix. It's symmetric and you have positive definite. So this guy is a convex problem. So you got convexity. Isn't that amazing? All right, good. So by weak duality, you have this lower bound. And the way you obtain it, we're not going to talk about it, but it's a good heuristic. You take its maximum over all lambda. Okay, so once you take the maximum, in most cases, this is attained. Okay, and it's called strong duality. All right. We'll talk about it next week because we're going to do inequality constraints. So I will give you the full theorem so you can just use it in the future. That's why I'm not giving all the proofs here yet. Next week we'll do it. All right. So now let's solve the dual problem. All right. This is the dual problem, so let's solve it. So meaning you have to find the maximum of this or the minimum by having the minuses out. And we've done this before. So this problem, which is just the minimum of half lambda A lambda plus B lambda. This is convex. And we found it before, right? It was this guy. Do you remember? So this was the minimizer for this problem or the maximizer for this problem. Same thing. Okay. All right, good. So you plug it in and you get your D star. And this D star will be a lower bound for the P star. P star is the of x squared given that AX is B. Okay. So again, let me repeat what happened here. We went from a constraint problem. This is constraint to an unconstrained problem over here. Okay. There's no constraint here. All right. And if you remember from last time, constraints are very annoying. You have to find boundary conditions, increasing gradient. It was a nightmare. No constraints here. You just take a Hessian and you're done. You have no dot with this tangent space, none of that. You just solve a Hessian matrix, and that's it. And that gives you, but you pay for it, that it only gives you a lower bound. But next week, I will give you some results that make this equal. Okay? It's called Slater's condition, and it's the same from linear programming. Same condition. All right. I'll do one more problem, and that's it. Okay, so physics people, statistics people, this is nice. So this is, if you know, like MLE, maximum log estimation, you get this kind of stuff, but you, instead of xi, you have like densities. Now the question is to maximize it or to minimize this guy. All right, okay, let's do it. First, you find the Lagrange dual. So you take your constraint. By the way, don't use this today. I know you can in the quiz, but don't. If you make the question like a 2-minute answer, so I specifically said do not use Lagrange multipliers. But we can do it after in the midterm, yeah, and next week. So you put it over here. This is the Lagrange dual, meaning you take your function and you just do lambda times the constraint. All right. Yeah, I'll speed up. I'll do it quick. There's this amazing fact that when variables are separated, so if you take infimum over xy of gx plus hy, this is the same as the summation of them. Okay, so we're using this fact. Is that okay? So because they're separated variables. So be careful, right? This is not always true. Infimum is not linear. We're not using linearity. I shouldn't even write linearity because this is confusing. All we're saying is this guy does not depend on y, this guy does not depend on x, so you can separate. So again, the dual problem already became much easier. So now instead of studying the infimum of all of them, I just study the infimum of one of them. X is now a real number. Let me go back to first year calculus. So I did this and I found the minimum. That's the minimum of this guy. I just took one derivative, set it to 0, and I got my answer. So I set f prime to be 0, and it gave me this. Nothing hard. And then you plug in, yeah, so I plugged it in over here. So I have n of them, right? So you're going to have summation of the infimum of these guys. So that's how I got -1 n. And the lambda was from here. All right. Anyhow, I'll just finish here. So, so in other words, the dual problem, now that you found G lambda, is again to find the maximum of this. But again, this is first year calculus, and I found it. So now this gave me that it tells me that the maximum P star is lower bound by log 1 over n, which is amazing. Just think about it. I'll find you a lower bound of this crazy looking problem. Yeah. All right. Thank you. Good luck. All the best. Huh? Yeah. So you mean from duality or what? There's no, is goes. You said the example, right? Yeah. Oh, that example, yes, over here. Yeah. I mean, it's the same thing. Yeah. So this is the guy, right? The same guy. I took his gradient and from the stationary point to find the stationary point. So I can plug it in here because I want to find the infinity. So it's convex. It has a unique global minimum, and that global minimum is given by the stationary point. No, just x, because we're taking an infinity x. Yeah. Yeah. Right, and then so it's convex max. It has a unique global minimum, and I'll find which is this. This is the unique global minimum, and I just plugged it in, and he gave me the formula. So it's in the next. So you plug it in, and you get the dual function. They are. I don't know why I put them. Do you remember the plane method from you have that simplex, and then you had like a plane that was moving? Huh? I don't know however you call it, but do you remember you had like a simplex, and you had like some tangent line, and the first point that it hits was like the minimizer. Yeah, so it's the same sort of thing. Uh, you maximize G lambda. So, okay, what is this picture? The guy, yeah, so T is the function, and U is the constraint. U is the constraint, T is the function, and Um, so this picture proves the big duality. So it says that even if your problem is not convex, um, the maximum of G lambda will be a lower bound for the minimizer. So this is the minimizer for the function, P star. And it says that the maximum of G lambda will always be at most that. The G lambda is the Lagrangian dual. Yeah. And the set G is given by the constraint and the prior. So this is why I didn't talk about it. This is a bit confusing. Yeah, U will be the constraint. I mean, it will be so your x variable is the constraint. Like this is the constraint. You have one constraint equal to 0, this guy. And this guy, the t is the value minimum. Yeah, and u is equal to h1x, yeah. Right, but you I mean, that's why I didn't talk about it, because this one is about less or equal than 0. So this is for next week. Yeah. That's why we get, otherwise you just get a line. Yes. Yes. Yes, yeah, because it will be negative. That's right. Yeah. So it's the same. I mean, I will do it later. Because I want to, I mean, I will talk about it next week because I want to draw the picture from 2 through 6. But it was the same thing that so yeah, so lambda is the slope of this, and we're taking maximum in lambda. This is the dual problem. I mean, anyways, you take maximum of the slope, and as the slope increases, eventually you get this point, which is the minimizer. Okay, so the what? G lambda is, I mean, G lambda is given by this. So, wait. So, G lambda is the guy we talked about it before, the Lagrangian dual. So, this is a constant that depends, it's the infimum of this plus lambda of this. Yeah, in lambda. Yeah, yeah. And we just proved that. Yeah, it will change, but we proved that this guy is always below P star. Like that's what we proved today. Like we proved this. This is not from the picture, this is from our proof. That this guy is always less than this. So, and that's why the line will always be below it. And this picture shows that they might not be equal, right? Because as you move higher and higher, you see, because the problem is not convex, it will go like this, and G lambda will not hit the star. Yeah. So you need convexity. So this line Yeah, because of G lambda, because G lambda is not allowed to hit P-star. It's not allowed to procrastinate. What's the what? I mean, we'll talk about it next week, but this is like you transform. I don't know if you remember. You take the domain D and you transform it by these variables. But all you care about is that the vertical plates are given by f(x). And so this guy will be the minimum. Because you want h1 of x to be negative. This is not the minimum because I'll talk about it. You want this guy to be negative. So this is the minimum of the negative. Oh yeah. So I mean, we'll go back to you the last 3 weeks where you only like that. And that would just be a physics problem. Because but yeah, like I'm happy we're doing this now because the Lagrange from physics is a infinite dimensional thing of this. So there you take infimum over functions, okay, and you move to a dual problem. But anyways, I mean, remember you have this integral and you like take a Frechet derivative. How do you call it? Yeah. I mean, you have this, yes, but how do you get the differential equation? Remember, you have Euler-Lagrange equation. Yeah, so you start with the action, you need to go and you take the multiple of Frechet derivative. Yes, you take a functional analytic derivative, and that gives you the Euler-Lagrange PDE. Yeah, we're gonna do that. But all I'm saying is that the thing we're doing over here is like a finite dimensional analog of Lagrange multipliers. Yeah.
So you just have a like ingredient of that. So in like if the 3F is a multiple of 3H, that means like each water the type of things you can expect happen. So like 3F less than the sample. So the case is just the 3F less than the so yeah, so I agree. Yes, so if we have not
we have to stay in the one